This is the video for our CVPR 2023 paper, VoxelNeXt, fully sparse VoxelNet for 3D object detection and tracking. 3D object detectors usually rely on anchors or centers, and translate well-studied 2D frameworks to 3D. Thus, sparse voxel features need to be densified and processed by dense prediction heads, which inevitably costs extra computation. In this paper, we propose VoxelNeXt for fully sparse 3D object detection. It is an elegant and efficient framework, with no need for sparse to dense conversion or NMS post-processing. Dense head tradition usually leads to inefficiency. We visualize the heat map in center point. It is clear that a large portion of space has nearly zero prediction scores. Due to inherent sparsity and many background points, only a very small number of points have responses. However, the dense prediction head computes over all positions in the feature map, as required by the dense convolution computation. This is a waste of much computation. In this paper, we instead propose VoxelNeXt. The key advantage is that our approach can get rid of anchor proxies, sparse to dense conversion, region proposal networks, and other complicated components. In the following, we introduce 4 detailed designs that contributes performance and efficiency. The first is 2 additional downsamplings layers in the sparse convolutional backbone. Strong feature representation with sufficient receptive fields is a must to ensure direct and correct prediction upon sparse voxel features. We make as little as possible modification, only using additional downsampling layers. We visualize the effective receptive fields. With additional downsampling layers, ERFs are larger and the predicted box is more accurate. In VoxelNet, we find that 2D sparse features are efficient for prediction. Height compression in VoxelNeXt is fully sparse. We simply put all voxels onto the ground and sum up features in the same positions. We find that prediction upon the compressed 2D sparse features cost less than using 3D ones. It is common that 3D scenes contain a large number of background points that is redundant and have little benefit for prediction. We gradually prune irrelevant voxels along downsampling layers. The voxel pruning largely saves computation without compromising performance. During inference, we can avoid NMS post-processing by using sparse max pooling, as features are sparse enough. We adopt sparse max pooling to select voxels with spatially local maximums. The removed voxels will be excluded in box prediction, which saves the computation of head. Our framework is naturally extended to 3D tracking. We record the position of voxel that is used to predict each box. Similar to the center association, we compute the L2 distance for matching. We empirically show that voxel association improves tracking. In VoxelNeXt, voxels for box prediction are not required to be inside the boxes, not to mention centers. We count the relative of voxels that are inside the 3D bounding boxes they generate. Statistically, only a few boxes, less than 10% in total, are predicted based on the voxels near object centers. VoxelNeXt has 4.9% less orientation error than centerpoint. We suppose that this results from that sparse voxel features might be more sensitive to orientation difference. Our model achieves good detection performance and outperforms all existing lidar methods on the nuScenes tracking test benchmark. It also achieves good results on Waymo dataset. Argovers 2 is a long-range dataset. Its perception range is 200 meters. The dense head method centerpoint has a high latency due to the large dense BEV feature map. Our fully sparse method performs much better. In this paper, we have presented a fully sparse and voxel-based framework for 3D object detection and tracking. It is with simple techniques, run fast with no much extra cost, and works in an elegant manner. For the first time, we show that direct voxel-based prediction is feasible and effective. In addition, we also extend VoxelNeXt with segment anything for promptable 3D object detection. Thanks for your listening. If you have any question, please feel free to contact us via email or open issues in the GitHub.